Hello and welcome to Procedural World Building in Houdini. My name is James Hodgart, and over the course of the next 8 weeks we will be exploring everything you'll need to start building your own procedural worlds in Houdini. So a quick word about me. I've worked professionally in Houdini now for almost a decade. I'm currently at Walt Disney Animation in Vancouver, and previously I was at Industrial Light and Magic and Axis Studios. I've used Houdini in all these positions as my main tool, and as a generalist I've spent many years exploring all the features and workflows in Houdini and everything that Houdini has to offer, and I hope in this course that I can bring some of those to you. So let's take a quick look at the course overview. In week 1, we'll talk about proceduralism in Houdini. We'll go through the procedural network examples, SOPs and channel referencing, curves, orientation, tangents, booleans for each loop, some vecs, and groups, cleaning and caching. In week 2, we'll start to build our procedural setup for our building, or at least one of the buildings that we have in our scene. And we'll use this as a study, going through floors, walls, windows and doors, roofs, extra details, adding varying materials and caching it out. After which we'll move on to creating an interactive HDA, one that you could use as and package up and pass to other artists. And at the end of that week, we'll move on to a hero building study where we're using procedural techniques to build assets that can be seen close up. Once we've got the buildings out the way, we'll move on to the landscape and the layout, setting up some cameras, looking at height fields and mountain SOPs in Houdini before moving into Gaia, bringing Gaia back into Houdini, and also using satellite data to generate landscapes in Houdini as another option. The second half of the course, starting on week 5, will be some more world building. So we're talking here about point scatters, instances, scattering on curves, using vecs to change attributes and manipulate attributes, taking a quick look at if statements, and using these techniques to create procedural city blocks and procedural roads. Week 6 will be Vellum. That's Houdini's more user-friendly effects tools. We'll be looking at the cloth, some wire and pin constraints, soft and rigid bodies, and we'll be using a marketplace as an example. So I'll show you soon the reference, but we're using a marketplace as an example of how to use Vellum. In week 7, we'll look at more procedural city elements, hanging wires, using Houdini nodes to build high poly bridges, some procedural docks, and how to add snow using VDBs. And finally, we'll cover ACEs. We'll explain more what ACEs is in week 8. Layout and lighting setups, adding vegetation to the scene, standard materials, procedural materials, cryptomats, AOVs rendering, and slap comps in Nuke. So week 8 is fairly heavy in information, but this is just a summary and a bit of an expansion on what we covered in the previous course. And in the end, you'll have a complete scene that is ready to go. So if we look at what happens each week, I wanted to quickly touch on the previous course. It covers a lot of what you see there in week 8, but over an entire course. So if you have already taken that, that would put you in good stead for what's coming in this course. But in general, this is not a beginner's course. We expect some level of skill within Houdini, at least basic knowledge of how to use Houdini as a package. Now, week by week, we will cover various concepts, and the first lesson will normally be an introduction to this concept, followed by working through examples. And in later weeks, if we look back, we will focus on more specific project-related tasks. After which, there will be some homework. And this will normally be working on your own scene, or it could be various case studies or some extra work that we, as we're working through the course and talking to each other, and we get to know what it is that you need as a student, we can facilitate some more specific homework for you. So finally, I just wanted to talk about choosing a project throughout this course. So here we are in PureRef. If you haven't seen PureRef or used PureRef before, it's a free package. Let me just bring up the website that you can download from pureref.com. And it is a massive canvas where you can store your reference and organize them into groups for easy access. So if we were choosing our scene, what we're looking for is something like this. We're looking for cities that have similar architecture, multiple variations of similar architecture. In that way, we can build one tool that will cover the characteristics of a certain style, and we can use that to generate multiple variations that we can populate a city with. So here's some good examples. So when you're thinking of your own, try and keep this in mind. For me, and during this course, I was looking at something a bit more Ottoman and Eastern European inspired, North African inspired. So I'm taking these type of architectural details and I'll be using these to build various procedural setups in which I can generate multiple variations of these types of buildings. And then we can see here the marketplace and the type of thing that we're going to use vellum for. All this cloth and scene assembly. Okay. So that's it for week 1, and I hope this has got you thinking about what it is that you might want to do in this course. And after this quick intro, the next video will just be covering proceduralism and the basics of what proceduralism is as a concept and how we use that in production. Thank you. Now let's start by talking about what we mean by proceduralism. Some pipelines use the word procedural in different ways. But what do we mean in this context? In this course, when we talk about proceduralism, we will be talking about the process of building setups that generate models, layouts, landscapes, or shaders. That's the distinct difference between traditional 3D modeling and procedural modeling. We will rarely, if ever, manipulate anything manually. Instead, we develop workflows that allow these changes to propagate through the setups automatically. The main mental shift you have to make, if you've never built anything procedurally before, is it's best to think about it like this. Instead of manipulating vertices, edges, and polygons into the desired form, we build a tool or setup that generates that form with infinite variation and minimal effort once the tool is made. So the first question is, what is proceduralism? It's a technique to build setups that allow us to change parameters that affect the final result. It can be used in modeling, surfacing effects, and animation. Actually, it can be used in most departments. It's made in programs like Houdini using nodes that are affected and changed by other nodes. Now this requires the mindset shift we spoke about, from thinking about modelling from A to B by manipulating geometry, to building a setup that takes care of those steps for you. Why is the next question. Using procedural setups allow us to create non-destructive workflows. These setups mean we have the ability to create infinitely changeable or randomizable objects such as buildings, trees, rocks, or any other object that requires many variations. And coupled with Houdini's node and instancing workflow, we can create complex looking scenes and objects that are interesting and efficient. Okay, when do we use proceduralism? Whenever we have a situation like a city, complicated buildings, or set dressing. We can also use it when creating any asset that doesn't require very specific high poly modelling to make our setup very flexible. Effectively, whenever the asset or layout will be subject to revisions or reviews, which is in most professional cases, having the ability to make quick changes without remodelling is always worth considering as an approach. So how do we do this? Houdini is one way. It's not the only program to create procedural setups, but it is one of the best. In Houdini, we use expressions, channel references, and vex in surface operators, wrangles, and vops. We'll go through what all these words mean as we progress. So we use these to build an interdependent network where changing the settings of one attribute affects another. In the end, we have some simple controls that completely change the overall look and shape of an object. Now we have some pros and cons, of course. One of the pros is that one setup allows us to create many variants. Procedural workflows mean quick revisions and iterations, which can make artistic feedback faster to implement. Setups can be reused and improved over time for multiple projects. Setups can be used by any level of artist once they have been created. It can save a lot of time if variants are the main goal. And procedural setups with instance geometry can save on memory and speed up rendering time. The cons are, of course, it takes a long time to learn how to build a procedural setup. The learning curve can be steep if you're not familiar with node-based workflows. It can be difficult to achieve very specific shapes and forms. Setups can become messy, overly complicated, making it very difficult for anyone but the artist who built it, or someone of a similar skill level, to make these changes easily. And surfacing procedural objects also requires procedural shading solutions, which adds to the complexity. Now we're all on the same page, let's quickly recap what we want to cover this week. Week 1 will be about starting small and working through the main tools that we use whilst building procedural networks. None of this will be too advanced, so a basic understanding of Houdini should be more than enough to get started here. And we'll talk about why we're covering each one of these as we move through the lessons. So this week it will be Procedural Networks Overview. We'll just take a quick glance at what a procedural network looks like within Houdini. Then we'll move on to the lessons, so SOPs and channel referencing, curves and point orientations, groups, copying and booleans, vex and vops, for each loops and SOPs, cleaning and caching, and then some homework afterwards. Okay, so let's move on and take a look at a procedural network. So I thought it would be a good idea to just take a quick look at a procedural setup that we have already. This one is for the procedural buildings that we created, just in case anyone here hasn't seen a procedural network before, you know what to expect as we go forward. So if I jump inside, we have a whole bunch of nodes. Each one of these nodes does a little change or a little addition. So although it may look complicated, once you understand what's going on here, it's not actually that complicated. It's just a lot of nodes, each doing its own thing. So what we have is some organization from the first floors and the doorways and the windows all the way to the roofs on the side, which are all generated from one input geometry. We actually have that input geometry here. It's just a curve. If I hide this, it's just a curve. And depending on what this curve looks like, it is then brought back in, has some materials applied. And then we use that as the final result to switch between the in progress building and the cached version. All of these nodes are controlled by this control node that we set up, and each one of these nodes have some sort of reliance on these sliders here, which are exposed and promoted to the top level here. That means that when we change one thing, if we change the floors for instance, this is updated, and whichever nodes correspond to this change are also updated. This is what we mean about the automatic propagation of changes by changing one channel that affects many channels. So in the end we have this node. This is an asset that we create, and we can pass this asset to other artists, other projects. They can open it up, they can make their own changes, save a new asset, and that's how we begin to build our own procedural networks, our own custom procedural networks. Okay, so I just wanted to take a look, or at least demonstrate what this looks like. So as we're moving through our videos, you can see what the end goal might be. Okay, so that's enough for getting an idea around what proceduralism is. And I think it's probably time we start learning some of this stuff. So the next lesson will be covering SOPs and channel referencing. So that starts at the very foundation. The first thing we want to talk about are SOPs and channel referencing. To begin, SOPs are surface operators. These are any nodes that create or modify geometry. So let's start with a tube. These nodes contain channels here, and channels can be changed to change the look of an object, like this. Again, very basic, but it's good to clear up any of this terminology. To make our first steps towards building a procedural network, we will reference one of these channels to another. This means when we change one channel, it will change the other. Now this is the basics. Let's build a basic pillar as an example using this tube node. So a simple example of this would be keeping the bottom of this pillar here on the ground plane. So with the height set as 1, if we want to put the base of this on the ground, we set this center to 0.5. If the height is 2, then we set the center to 1. So this is the foundation of procedural modeling. That is looking for relationships between certain channels and how they affect each other. Now we can see, again, if I change this to 3, this needs to be 1.5 to set the base on the ground plane. This means the relationship between the height and the center Y position is 1/2. So whatever the height is, if we set this to 1/2, the base will always be set to the ground. So in that case, we can reference this here to this height. This is also known as channel referencing. So we have a couple of ways we can do this. We can right click and copy this and paste the relative reference. That's one way. The other way is we can drag this in here and press relative channel reference. Or we can go ahead and type that same piece of information directly into the channel itself. So that's the 3 ways in which we can do this. Let's take a little look at what this actually means. So what we see is the CH bracket quotations height quotations bracket. And what does this mean? Now CH is known as an expression, and that refers to any channel defined by this name, in this case height. If you hover over any channel label, you can see what the name of that channel is. Hovering over height, we can see that that parameter is called height, in this case with a lowercase at the start. We will look at some more expressions later and how to use them. So we know this center Y needs to be 1/2. So what we can do is just add /. This is the divide operator, and press 2. So now, no matter what we change here in the height, the base will always be stuck to the floor. That is proceduralism in a very small example. So let me just set this to 2. Since we're making a pillar, let's make it look a little bit more like a pillar. Maybe point. Oops. So this is channel referencing within the same node, but we can channel reference between nodes. So if I drop down, say, a box, set these so they are smaller, what I can do is I can use that same process. I can copy this parameter, go to the box, and in the center Y position, I can paste that relative reference. I'll use a merge node just to bring these back together. Oh, a little 0 ended up in here. I'll just remove that. And now we can see that these two nodes are linked. Again, we have the channel reference. This is looking within the setup here for the node called tube1, and it's looking for that label height. Again, we'll go into more detail as to what these things mean, but for now, if we change the height, this box now follows. Now we can do some pretty amazing stuff with channel referencing, and we will. So don't worry, all of these lessons aren't as simple as this one. I just wanted to ease us in, but we'll ramp up pretty quickly. So next up will be a longer lesson on curves, orientation and tangents, as they are very integral to most of our setups. Curves are one of the foundations of our workflow. We use them all the way through our setups as a way of creating geometry for pipes, wires and frames, to generate geometry from floor plans, and most importantly, to create points as a base for our scatters. There are many more examples of where they're used. So here we have a few examples, like we just discussed. We have a curve that's being used to create a pipe, a curve that's being used to create a floor, and a curve that's being used as a basis to copy objects to. We'll have a whole demonstration on the copy SOP, so you don't have to worry about what's happening here yet. Now, generating curves is easy enough. The most simple way is to use the curve node. We just have to click to add points, drag to add tangent handles, and right click to finish adding the points. We can also switch to the cursor mode to move points around, and control click to add some new tangent handles. What we are really interested in here is the points. So if I switch to this curve here, we have the points. At the moment it's set to polygon mode. It could also be Bezier curve, but we'll leave it as polygon for now. And we resample this edge so we can get more points along and control how many points that we have. The resample node adds points along the curve, and you can change how many points are on the curve, and also whether or not the curve is set to straight or subdivided. So these points have no orientation, but we can create the orientation ourselves. If we look at what an object looks like copied to these points, in this case just a vector helper, you can see it doesn't actually align to the curve at all. It just all points in the same direction. Now, if we use an orient along curve node, we automatically set this up. So these objects now follow the flow of the curve. And this is also reflected here. We can see it now has a normal and an up vector, or two vectors, a normal and an up vector. Again, we'll discuss what all of this means, but you can see that before, only one point attribute exists. Afterwards, we now have a couple of new attributes. We can also change the additional rotations if we want to spin these around a bit. Now, this used to be very difficult. It used to be something you'd set up manually, but this new orientate along curve node really does make this easy. Now, this helps us a lot. It gets us most of the way there. But one thing we want to be able to do is better understand what's happening here and better control what's happening here to do things like add random rotations. But we'll come back to that later. This seems pretty simple, but there is a lot going on under the hood, and it takes a lot of explaining. So once we've passed through the basics, we'll go back and we'll explore all of these. All you need to know for now is how to create these new point orientations using this orientate along curve node. So when we copy objects to these points, they flow well. So next, let's take a look at groups, the copy swap, and using booleans too. The copy swap will be one of the staples of our procedural setups. This too has had a revamp in more recent Houdini versions, so we will start with this workflow and discuss breaking it down in later lessons as an exercise. So we have our input points with the correct orientations, and we have our pillar. I've just gone ahead, scaled down the bottom points here using an edit node. If you don't know how to do that, just drop down an edit node. You can switch to points here, grab these guys, and then just use a normal scale to scale them in. Okay, so yep, we have the pillar and we have the points. Let's drop down a copy swap. Copy to points. The geometry goes in the left hand side. The points goes in the right hand side. And we can see that due to our orient along curves node, that the pillars flow nicely. So a copy swap in general takes any import geometry on the left and copies it to any existing points on the right. It can also be left as full geometry, or it can be instanced to make it more efficient. That has some pros and cons. We'll talk about them later. So although it looks basic, a copy swap can be very powerful, especially when used alongside point attributes. This means that rather than the output geometry just being copies of the original, we can add variations based on the original, varying the size, the rotation, the color, etc. For now, let's look at groups and come back to these later. Now, group nodes seem simple, but they are very powerful in a procedural setup. We use the group node to establish some rules, such as objects with certain names, facing angles, open edges, matching attributes, or even by bounding object. Once we've got the group, we use it as we like, so we can use it to manipulate the geometry, to delete objects, apply materials, create UVs, many things. Let us run through an example of one way we'll use it in our procedural setups. Now, if we look at the group node, just drop one down, we can name the group. In this case, it's set to group 1. Let me just plug this in here. we can choose whether it points to primitives, points, edges, or vertices, and pick what type of operation we want to perform. So we can replace an existing one, we can add it to an existing one, intersect, subtractions. We will use all of these at some point. But in this case, we can leave it as replace existing. We can also narrow the scope of this to only affect existing groups or pre-existing groups that we created before. We can leave this empty for now. And below here is actually the option I want to use, keep in bounding regions. Again, we'll look at the rest as we go, but yeah, let's stick to this one here. So we have the pillars. At the moment, it's copied to each point that exists. Let me just reduce this to 6. But what if we only wanted these pillars on every second point? And that would allow us to create something else for every other point, say a doorway. Again, there are 100 ways to do everything in Houdini, but let's go through an example, a Soop based example, that also utilizes the copy Soop. So we will go through one step at a time. One way to quickly add more points to a curve is just to subdivide it. So if I switch to this one, drop down a subdivide node. I'll actually put this in before. We get a new point between each existing point. So what we would like to do is have a group made up of the original points, like here. Switch this to points. Let's call this pillars. And enable this base group, or at least make sure that it is enabled. And then, if we plug this into the subdivide node, what we want to happen is we still have this existing group. As we can see, that doesn't happen. So how can we retain this group throughout this? This is where we spoke about the bounding regions option on a group node. So if we add a copy Soop, and we add some spheres to these original points, like this. Let's make these a bit smaller, they are a bit big. We now have a sphere for each of the original points. Just move this to the side. And we have the subdivided points, or the subdivided line. So now if we add a group node, and in this second option, this is where we add the bounding objects. Set this to points again. Disable the base group, and instead enable keep in bounding regions, and set this to the bounding object. We can see that we have a new group that contains only every second point. So we can get rid of this original one and call this one pillars. Awesome. So we now have a way to differentiate every second point. If we go to the copy to points node, we can see that each point on this resampled curve is currently getting the pillars, but we can instead specify only the pillars group. Great. That means we have a curve where every second point is free. So let's say we just wanted to copy a box to this. And let's make it doorway shaped, so just make it thinner and taller. And we'll use our channel reference again to make sure the base is always on the ground. Sorry, so copy from the size, to the center Y, and half it. So we have these groups here. How do we only get these points and remove these points? Well, that's easy. We can use a blast. A blast to remove the points, and set this to pillars. So now we have an option where we have a line that only has every second point, and a line that has the points for the pillars. So now we can use another copy. Use only the blasted points. And in this case, we want it to happen after the orientate along curve node, so we can get the correct orientations. And now we can merge these back together. Cool. So now we have a variation here, pillars and boxes. So that's one way to do it. Again, there's loads of ways to do this, but this was a nice demonstration. What if we, instead of having a box on every second node, we actually wanted to have a wall where each one of these box positions was a doorway. So to do that, we need booleans. And what we're going to do now is we're going to use the sweep node or the poly extrude node to create a wall, and then we'll use the boolean node to boolean each one of these doorways out of that wall. Okay, so the first thing we want to do is build our wall, and to do that we will first use the sweep node. Just drop this down here and use this curve. That's the curve before the scatters. And the sweep curve starts off as, it always has this warning. You just have to change, if you don't have any second input, you just have to change this to one of these other options. For us, let's grab the ribbon, and you can see we have some thickness to our curve. Let's see what the geometry looks like. We have too many segments here, so let's just reduce them to just 1. And we also want some height. So for this, we'll use poly extrude node. And we'll up the distance. Let's merge this back in. So let's keep this procedural again, and we will channel reference the height of the column. Let's just grab this height here, copy this, to the extrusion distance. So we can make sure that the height of the wall is always the same as the height of the columns. Awesome. And we can control the thickness here using the width. Make it a bit thinner. Okay, so what we want to do now is use these boxes, and instead of them being just merged, we want them to be subtracted from the wall. And we have the boolean node to do this. It's very powerful, very easy to use. So we use the boolean node. Let's just remove this. We plug geometry A into here, which will be our wall, our doorways, and geometry B into here. We just want to make sure that this second input here is a complete geometry. So at the moment it has a hole in the bottom. We just want to make sure output back is enabled in the poly extrude. And then if we go back to the boolean node, we can set this from A to B to B to A. And make sure that this is thick enough. So let me just add some more thickness here. This direction, I think. Awesome. So now we have these doorways booleaned out from the geometry. So the geometry itself is a little dodgy looking if you're used to high poly modeling. This type of geometry might look a bit broken, but it actually renders just fine. Arnold Mantra Redshift will render this just fine. So instead, let's just plug this into the merge node. And now we have some doorways. Again, these doorways can be changed at any time, just by changing the size, or the width. This way, sorry. Awesome. The next thing I want to talk about is varying these. We spoke before about varying the P scale using some attributes. So let's do that. All we need to do is before our copy, so before we copy the pillars, we want to drop down a attribute randomize and set this to P scale. Now P scale is an attribute that already exists, and we can just manipulate it using this attribute randomize node. So some of them are getting very small, as you can see. Very, very small. So instead of this being between 0 and 1, we'll change this to 1 dimension and make it between 1 and something closer, 0.9 maybe. Now we have a little bit of variation going along. So that's one type of variation, but what if we wanted each one of these pillars, or maybe every second pillar, to be a little different? Let's talk about varying those up. Okay, so as we said, in a lot of cases we want to add multiple variations of the input geometry and cycle them through on the output. For this, we need to name each object and use the attribute from pieces SOP along with the copy SOP. So I've gone ahead, created a new pillar here. The only addition is this extra cylinder in the middle here. And what we need is to name one of these, or to name each of these. So there are many ways to create a new attribute, but for now we'll just use the name. We'll name this one pillar A, leave this name for the moment, and we'll call this one pillar A. We'll call this one pillar B. And then we will merge these both together. Awesome. So the node that we said we need is the attribute from pieces. This guy here. And this will add a new attribute to these points which cycles through whatever we have named here. So we have the point cloud in the geometry library. Point cloud goes in here. Geometry library goes in here. And this goes into the right side of the copy SOP. So at the moment, all we are getting is the second output. If we go to here, it's already set to name. If we go to the copy to points, we can enable piece attribute and set this to name. And you'll notice that nothing is happening. This is because each one of these points, or this attribute from pieces, is being created on all of these points. And then we are specifying that we only want these pillars on every second point. So what's happening is you're seeing pillar A, pillar B, pillar A, pillar B. And then when we go to the group node, we're actually only getting every second point, so we're only enabling pillar A or pillar B, say, whichever attribute is on this point. To get a better look at this, let's look at the geometry spreadsheet. If you're not familiar with the geometry spreadsheet, this is just a way for you to better visualize what's happening on each one of these points when it comes to the attributes that make them up. So if we look at these points, we have the P for position, the N for normal, we'll have the up. Both of these were created when we created the orient along curve node. But we also have the name, AB. So this is created from this attribute from pieces node. So as we can see, every second point is getting a variation, and then when we move to the copy to points, we are only using every second point. If I disable this, so we are targeting no group, you can see it works just fine. So what do? We obviously want to use this pillars group, but we want it to be varied across this. We'll just use the blast node again. But in this case, we'll use the opposite. So plug this in here. And instead of delete selected, which is what is happening right now, we'll use delete non-selected. So now when it comes back to the end, we're getting that variation again. Awesome. So now we have what we want. We have our wall, we have our doorways boolean through, we have our pillars, they're varied for each point. But what we want to do is just adjust the P scale a bit. It's a bit too extreme. Let's just take this to 9.8. So this works just great. We can use the attribute from pieces node to change it a little bit. We can offset it. Instead of cycle, we can use random. We can set it to noise patches. Lots of cool stuff. But I think that's enough for now. So we're starting to see our procedural network grow. And as mentioned in the video, when we looked at the huge procedural network that created the building, you can see how quickly it starts to become a little bit more complicated at first glance. But once you start to know what each node is doing, it's not so complicated. This video will be on Vex and VOPs, and it will be a little longer and could be much longer. Before we go too far, I just want to have a quick recap on what's happening here in Houdini and how we treat geometry and access geometry. Now, in Houdini, like any other computer graphics program, we manipulate geometry. This is points and vertices, edges, polygons, and objects, whilst modelling. As we already spoke about before, whilst modelling procedurally in Houdini, we require a shift in thinking. Rather than directly modelling and moving components around, it's often better to think about it as indirectly manipulating the geometry. And how we do that is by accessing the information that makes up the components. In its most simple form, a point has only P, its position in space. We can add anything we like to this or vary it by another attribute. To cover some ground that we already began in one of the last videos, Houdini makes this very easy by giving us the use of the geometry spreadsheet. This is a complete list of all the attributes that correspond or make up a component and the value of that attribute. There are many ways to manipulate geometry in Houdini, but the three main ways are SOPs, Vex, and VOPs. SOPs are surface operators, and they are most nodes, like the transform node for instance. Vex is the programming language that we use inside of Houdini, or one of the programming languages, and we can also use this to modify geometry, components, attributes, and groups directly. We can also use it for creating shaders and a few more things. VOPs, or vector operators, are a more visual way of accessing the component level attribute changes, and again can be used to manipulate geometry and apply mathematical operations. So I guess we can start with why use each one of these. SOPs can get us most of the way there, and in a lot of cases it can get us all of the way there, but using a little or a lot of Vex here and there can speed up your process and make it much more efficient. It can also make it easier to make specific changes that would be difficult or complicated to do if all we had were SOPs. VOPs have a similar benefit, but are easier to manage for those who aren't comfortable writing in code, more like a visual programming version of VEX, as we mentioned. Each one of these nodes are doing the same thing. They are all transforming the pillar -1 on the Z axis, just in different ways. Now, SOPs are generally the slowest way to perform geometry changes. This is because that each node has a lot of features and channels, and each one requires computation to reach the end result, even if it's not in use. Side effects does an amazing job to keep them very efficient, so generally the pros far outweigh the cons when it comes to using them. VOPs let us go a little deeper, but these are still node-based. One of the benefits is that we don't have to input any code to start doing some more complicated work. Whereas with VEX, we can cut to the chase and only input what we need, or exactly what we need. Now, let's clear these away and rebuild them so we can see what is happening here. So the transform is easy enough. Transform node -1 on the Z. Easy. Now, when it comes to VOPs, we want to use the attribute VOP to access this. There are other VOPs, but attribute VOP is one of them. And within the attribute VOP, we have the existing attributes that exist per point, and we have the output attributes that we can use. So if we plug P straight into P, nothing happens because we haven't changed anything. So P is a vector. In this case, it has 3 components, and we can use a vector to float to split these channels. Here we go. We can also use a float to vector to collect these back into the vector. So this is X, Y, and Z. And again, nothing is going to change because the input values are the same as the output values. If we want to manipulate that Z component, we can add, let's just say we use an add constant node and filter this through. Awesome. So now we are moving it +1, but what we want to do is move it -1. Great. So now we have the same function. How do we do this in VEX? So we can drop down an attribute wrangle, and this is how we can access VEX. So I'll type in some code here. What we will do is go into some more detail in another example, but for now I'll just explain what I'm doing. So at for attribute P dot Z, that's the component that we want, is equal to, again, the current position, because we don't want to change it yet. We still want every point to be where it is right now. All we want to do is take all of those existing points and move them -1. Easy. So that's how we carry out the same transformation on one axis using the 3 different ways. What we can do is take it a bit further, and to demonstrate this, let's add some variation to the points before we copy the pillars onto those points. And we can also explain a bit more about what exactly is happening with VEX. So here we are back in our pillar setup, and what I want to do is drop down a wrangle just before the points that we copy the pillars onto. So within this wrangle, let me just type out the expression and then we can break it down and talk about exactly what the expression is. So again, we want the P attribute or the position attribute. In this case, dot y, we want that to be equal to the point number, which is randomized from 0 to 1 to 0 and 0.1. Okay, so that's what that looks like, and you can see we get a little bit of height variation on the pillars. So let's just explain a little bit about what is happening here. So again, we have the P attribute. We have two expressions, the fit 01 and the rand expression. Then we have a point number, and we finish off the fit expression with 0 and 1, and then we use a semicolon to end the line of code. So you might ask yourself, if you're new to this, how you arrive at this conclusion, like how you would put together this sort of line if you didn't have any information to go on from the start. So I think it's probably a good idea to jump back into Houdini, and let's construct this as if we were logically working through a problem. So back in Houdini, let's just clear this line. Okay, so we know how to access the P attribute at P for attribute P, and then we know that we want the Y attribute. But if we want to move this randomly, let me just jump back here. If we add just one, a single integer like 1, everything gets moved at the same time. Everything gets moved up by 1. But we don't want everything to be moved at the same time. We want it to be random. So we do have a random expression if I type in rand. And this is what I mean by logic. So if we were writing this on a bit of paper, this is what we would want to happen. We'd want it to be random. So it just so happens that, you know, a lot of these functions exist, and we can start typing them in. Now, if we type in a bracket, we start to see the help that is given to us to work out how to use these functions. We can also press F1 to open up the help menu. And again, we can see what this does. Creates a random number between 0 and 1 from a seed. So if we use this rand function and we type in any seed value, this is just any number, and press 1, we get a random value, and that random value changes depending on the seed, but unfortunately for what we want it to do, it's the same for every point. We want this to be different for every point. So we can use another attribute that exists. That's the point number. So if I type in at ptnum, now we get a different value for every point. That's because this new seed is running off the point number, and instead of it being the same for every point, as each point number is different for every point, the seed is different for every point. So now we have a new random number per point. Now it's too strong. We don't want it to be all the way down from 0 to 1. It's too high. So we have another function. We have the fit 01, and we can see that this takes a value that's in the range from 0 and 1 and shifts it to a new range that we can specify. So we actually do have a fit function which takes any range that we specify and rearranges it to a new range, fit 0, 1 assumes that the incoming range is already between 0 and 1 to start with. And if we go to random, we can see that random creates this number from 0 and 1. So we can take advantage of this to simplify the line, use the fit 0 from 0 between 0 and 1, and we want to remap this between 0 and 0.1. Awesome. So how did I know that it needs these two arguments at the end? If I go back into the help menu, we can see that it says the float value, which is in our case the random point number, and then between the minimum and the maximum. So that's what we have here, the minimum and the maximum. We can also take advantage of some of the expressions we learned previously by creating a new channel. So this channel doesn't exist, but if we want to say max, let's just call it max and close that off. It won't work because this channel max doesn't exist. We've just referenced a channel that doesn't exist. But if we press this button here, it will create a new channel underneath. So we can actually create channels in a few ways, but this is one of the easier ways. So if we press this, we have this new max, and then we can change this. We could also change, for instance, ptnum, and we can add any value to this, and this acts as a seed. Again, we can go so far as to paste this in here, call this seed, create this, and then we have this new seed. So the reason I wanted to go through this is mostly for anyone who maybe has never used Vex before, because we will use a lot of Vex, but it won't get much more complicated than this in a lot of cases. Some cases it will, but we will make sure to explain everything that we're doing whilst we're using Vex. So we won't get super deep in this course, but Rebelway does offer a really in-depth course on Vex by Corbin Main. It's really worth checking out if you're interested in this stuff and want to do a bit of a deep dive. Cool. So this is a really good start. The next thing we want to do is introduce some for each loops. This is because we don't always have the ability to access geometry, or want to have the ability to access geometry that's copied to points. Sometimes the geometry already exists, and we want to be able to do per object changes. So that's where the for each loop comes in very handy. So let's jump over to that. Okay, on to SOP based for each loops. Now, you might have heard of for each loops before if you have any programming background, but in this case we won't be using any Vex or any programming language. Houdini has a very useful SOP based version of the for each loop for us to use. So to demonstrate the functionality of the for each loop, let's add a row of bricks along the top of this wall here. The first thing we need to do is what we did before, drop down a copy to points, and we want that same curve that made up the wall. So let me find the curve. Is it this one here? Yep. And we want this curve to come in here to the points. Oops, wrong side. This one here. You might see I use this shortcut every now and again. It's just Y, and that allows you to drag out a line to disconnect these nodes. So we want this, and we want our brick. So let's say it's a box. Let's see the size. A bit big. Something more like this maybe. We can always rescale it later, and let's copy that to the points. Okay, maybe some more length here. Awesome. I also want to chamfer these bricks, why not? We can use a poly bevel. That's fine. Okay, so we have this row of bricks. Let's just merge this back in. Put it down here somewhere. And at the moment it is on the floor. What we can do is channel reference the position of this curve here to the height of the wall. So let's use the transform node and our poly extrude node and take the same distance and add it here. Cool. So of course there's some penetration here, but this is just for learning purposes, so this is fine. So if we had this geometry and we wanted to vary, let's just say its position on the Y. You know, we created this by using the existing points on the curve. If we wanted to vary this on the Y, we could just use this that we created before. But in a lot of cases, we don't have this copy to points. And in some cases, it's also not desirable. When we move into the full setup, you'll see instances where this is true. So let's use the for each loop, as it's very useful. So if I drop down for each, so what I want is the for each connected piece, and this also drops down a connectivity SOP. This connectivity SOP generates an attribute. It's defaulted to be called class, and this is used to define what is and what isn't a continuous mesh. So that means for all these connected points, each one gets its own ID. So if I go to here and look at the class, this first group up to 25 gets class 0, the second group up to 51 gets class 1, and so on and so forth. So this would be the first brick is 1, second brick is 2, etc, etc. So now we have an ID that we can use within the for each loop. So if I make this active at the base, so what we want to do is add some variation on the Y. And to do this, all we need to do is drop down, well, we'll use a transform node. We could have used the attribute wrangle, but we'll use a transform node. And we want to access each iteration. So if I check single pass, you can see we have each iteration along here. And all I need to do to access that information is create a meta node, which is here. So when we press this, we have this extra node. And if we click on this one, we can see that we now have some new detail attributes. Detail attributes are attributes that apply to the object itself rather than each individual component. And we can see that in the geometry spreadsheet if we go here. So now we have this iteration. And if we cycle through the different passes, we can see 0 is 0, 2 is 2, and so forth. So we now have a way, or some information, that we can use that changes the operation in here for each connected object, hence for each connected piece, for each loop. So if I go back to the scene view, make this active, disable this, we can access that detail attribute. Let's take a quick look at how to type this out. So this is what it will look like in the end. We have the expression, in this case detail, and what this does is it defines that we are looking for an attribute that is a detail attribute. We can also use point, prim, vertex, depending on where the attribute is. In this case, our attribute is a detail attribute. The string asks us the node location, So this node is called IT, and then the attribute name within that node. And finally, we're looking for the index. Now, you also notice that we don't have a semicolon here. We don't need that whilst we're working within the channels. So this will get us so far. Let's just go back to Houdini. Okay, so that was detail, the path to the node. We haven't renamed this yet, but we will in one second. The name of the attribute, you can see here, string, float, the surface node, attribute name, attribute index. So we need the name iteration and attribute index. This won't work yet until I do this. And make sure this node is called IT. So you can see we are getting the same type of effect that we did when we used point number. And that's because each iteration is getting another value of 1 applied as it goes. So this doesn't quite work. This isn't what we want. We can do the same thing as we did before, and that would be to use a fit range. But instead, let's look at another way in which we can do this. Because I know I'm happy for this value to be fairly low, I can use the rand expression again. And this will take this output and randomize each one between 0 and 1. Having tried this already, I also knew that even 1 was too high a number. So I used a multiplier to bring all the strength of that down. So let's see what that looks like in Houdini again. If I type rand and close this off, we get a nice random value for each brick. Between 0 and 1. But we also think that this is too strong, so shall we multiply this by 0.02. We can increase this as we like. And again, we could reference this to another channel, so it's a slider. So that's enough for each loops. Let's go ahead and wrap this up by cleaning up the network and exploring different ways to export the geometry. The last video for this week is cleaning and caching, two very important yet sometimes overlooked parts of the procedural pipeline. During the process, we tend to create lots of groups and attributes that may or may not get in the way as we go along. So it's good to know how to remove them once we've used them. This also reduces the size of any cached objects. And obviously cleaning is important because quite often your setups will be passed on to other artists, so they need to be able to navigate around your setup successfully without wasting too much time. So as we go to, the network will become more complicated, and it may be at certain intervals, definitely at the end, you want to save parts of the mesh out, just so you don't have to keep running through some processes as you go. We can use several nodes for this. We can use the alembic ROP output, and ROP means render operator. We can use the geometry output. We can use FBX. And we can even use USD if we want to. For me though, I will just be using Alembic, so let me get rid of this. So actually this wasn't the alembic output I put down. It was the alembic input, which I needed anyway. Let me just put an alembic output down. There we go. So this is the alembic output. Now in the alembic output, we would just choose our path. One thing we can do is we can copy this path as we did before and channel reference this here. And this means if we ever change this path, then our import path also changes. Let me just save this. And now when we bring the object back in, it automatically points towards this path. Now our normals look a bit broken. That's because it's being loaded as a delayed load primitive. We will do a lesson on what all this stuff means, but for now we can just unpack it and bring it back in as geometry. So let's talk about some hygiene. It's good practice to make sure that at the end of your node stream you have some indication of where things are supposed to end. So in this case, a null with the out label would be useful, or we can use the output node that also exists. The difference being that if we say flag anywhere else here and go up a level, the output node always tries to force this to be the final visible node, whereas the null just with the label out won't change when you go back up a level. So if I delete this output node, shift somewhere else, and go back up, it doesn't change. But either one is fine as long as you make sure that the display flag is on the right node. Let's look at some other ways to help organize these node structures. One of the most effective ways, and something that we will look into a lot more extensively, is the subnetwork. A subnet or subnetwork is a container with inputs and outputs. This means that we can take whole selections of nodes and collect them together to keep the network simpler, at least at first glance. If we grab everything here, except the input curve, and I will explain why in 1 second, we can press the subnet button and that gathers everything inside. What is really useful about the subnetwork is it has inputs and multiple inputs. So this means that whatever we plug into these inputs will run through the subnet. If we go here, you can see we can access these 4 inputs. And in this case, anything that is plugged into the first input is coming out here and going in to our first node. This is the basis of asset creation. There will be lessons on asset creation as we go. Another couple ways to help keep your networks clean, we can use network boxes. And that is this icon. And that is this icon here. So again, grab a selection of nodes, press this icon, and we can call this pillars. And now we know where the pillars are. We can even color this. We have this swatch icon here. We can just color this whatever we like. Of course, these colors also apply to the nodes. And we can change the node shapes by grabbing the shape palette here. So now we have some organization going on in here. I just want to get rid of all of the spare attributes and groups down here before we save the geometry out. So to do that, we want 2 nodes. One is the attribute delete, and the other is the group delete. So if we middle click to see the attributes that exist, you can see we have the name, P for position, we have the class, and then we have some pillar point groups. So within the attribute delete node, we can see the attributes that exist. If we want to clear all the attributes, we can just use asterisks. And this goes the same for the group node. So within the group node, we can see the groups that exist. And then if we want to delete all the groups, we just have to use the asterisk too. So that means that by the end, we have just the position, perhaps just the position and the normal. If we look here, we can see the memory is 123 kilobytes. If we save this, now we've stripped out the groups and the attributes, and check, it's dropped down to 100 kilobytes. So not a big difference for a small object, but over a huge scene, these type of deletions and hygiene tips and tricks help to make the object itself much lighter, and therefore the scene much lighter, render start faster, etc, etc. So it's always good to bear this stuff in mind as you go. So this about wraps up week 1. If I jump back up, I can now call this wall. And now, if I just split view this so you can see what's happening, I have my pillar asset. And now, if I jump back inside and make this live again by coming to this merge node here and grab my input curve points, I can move them around. And I have this interactive wall that we've created. So it's not perfect, of course, but it works quite well, and it gives us a good base for understanding what we will be doing as we go forward. Okay, so I think that about wraps up week 1. Covered a lot of ground. We've explored the foundations of procedural tool building and geometry manipulation. And over the next 7 weeks, we are going to refine this and make some pretty cool stuff. Okay, so for homework, it's really just working through this setup, trying some different examples, changing the amount of pillars, changing the amount of bricks, making windows instead of doors, etc, etc. It's really just getting very comfortable with what we've discussed here in the first week so we can take that stuff into the rest of the course. Thanks.